So last time we're talking about logistic regression, and we left on this kind of very interesting discussion about when should we use naive Bayes, when should we use logistic regression, what's the difference between the two in practice. So I want to pick up there, and then also talk today in addition about linear regression, which is another learning algorithm for computing real valued y's. Up till now, we're trying to learn functions from x to y where we have discrete valued y's. Okay, so just as a kind of quick logistic regression in one slide, what we basically talked about last lecture in one slide is this, that the idea of logistic regression, the way we motivated it, was to say, well, what if we make the same set of assumptions up here in the first bullet that we make for Gaussian naive Bayes, then let's derive the form of p of y given x, and we agreed, we derived it, it's this. And then we derived a gradient descent algorithm for estimating the weights w, or learning the weights w from the training data, that followed what principle? What principle were we following in choosing those weights? Right, it was just a variant of the maximum likelihood principle. That is, we set ourselves the goal of finding the weights that would make the data most likely. And the variant that we used was conditional likelihood instead of likelihood. That is, instead of making both the x's and the y's most probable by choosing our w, we instead just simplified it to the conditional likelihood so that we assume the x's are just given. We don't have to worry about their probability. And so we just chose the w's that maximize the conditional probability of the y's in our training set, given the observed x's in our training set. And so then we got that nice gradient descent rule. And in fact, there is the gradient ascent rule. And then we mentioned toward the end that, oh, well, we could also, instead of maximum likelihood, try to do a map estimate. Of course, anytime we're trying to do a map estimate, we have to make up some kind of prior on the parameters that we're trying to learn or estimate. And it turns out if we say that the prior we're going to use is that each weight follows a normal distribution with mean 0 and some variance sigma. If each weight does that, and here I've written it as if the whole vector of all weights follows, I can talk about a multivariate Gaussian. That is a Gaussian defined over multiple weights. That's why this I is here. It's the identity matrix. That's a detail we don't have to really worry about right now. You can think of this as just a set of normal distribution. We say every weight, w sub I, follows just a univariate normal distribution with mean 0 and variance sigma. And then it turns out, well, the derivation of the gradient ascent rule when we just worried about this quantity is up there. When we add in the prior, that gives us one more term. It's a very simple term. It's a term that every time we do a gradient step to update our estimate of wi, given the old estimate of wi, we add in this quantity. And again, this quantity is just the misallocated probability mass according to our prediction. But this new term is just a simple term that pushes the weight wi towards 0. If wi is, if we make these constants positive, then if wi is positive, we're going to subtract some fraction of wi from its old value, push it towards 0. If wi is negative, we're going to add something to it to push it towards 0. We're pushing it toward the mean of this prior that we put on it. Okay, so that's kind of a quick review of last time. And skip this, just saying the same thing. So Then we started talking about the question of should we use naive Bayes, should we use logistic regression, who cares, what's the difference? This is actually just one example of a more general trade-off between, or question that we can ask about different machine learning algorithms. In fact, people often, you'll hear the terminology generative classifiers or discriminative classifiers. Generally, if people talk about a generative classifier, naive Bayes is an example, what they mean is that that learning method assumes that there's some functional form for P of y and P of x given y. In the case of Gaussian naive Bayes, for example, we assume y is governed by a Bernoulli distribution, and P of x given y is governed by a Gaussian distribution. And then we estimate the parameters of those two things and use Bayes' rule to calculate, given a new x, what's the probability distribution over possible y's. On the other hand, in contrast, if we have a discriminative classifier, such as logistic regression, then we just instead assume some form for P of y given x. And that's what we did. And then we directly estimate those. So it turns out for any kind of probabilistic model, not just naive Bayes, we kind of have this choice of which of these two ways to go. And you can think of logistic regression and naive Bayes as a case study in that set of choices. I put this note here just to remind me to remind you that there is this kind of difference between how committed these two methods are to the conditional independence assumption. Naive Bayes uses the conditional independence assumption both when it's training and also when it's using Bayes' rules to classify a new example. On the other hand, if you think about logistic regression, we certainly assumed the conditional independence assumption when we derived what's the form of P of y given x. Right? We went through that derivation. We started with the conditional independence assumption. However, the training procedure, the gradient descent procedure that we derived, really did not involve any assumptions about conditional independence. So that gradient descent procedure is just going to find the best fitting weights, W0 through Wn, given the data. And there's nothing about that training procedure itself that commits to following conditional independence assumption. Yes?
But is conditional independence implicit? Like, so will it perform better when there is conditional independence and worse when there is no conditional independence?
Yes, so if conditional independence is satisfied, then we're going to get good performance from both of these algorithms, at least as the amount of training data approaches infinity. If it's not satisfied, then in a way, logistic regression has a little bit more flexibility to, a little more robustness to overcoming the false conditional independence assumption that we're making. Yep?
Looking at these definitions, can we say anything about which type of classifier is more prone to overfitting? Can you say, like, looking at these? Or?
Yeah, that's good. Overfitting is a funny problem. I'll just say this. Naive Bayes, as we talked about last time, is estimating more parameters than logistic regression, right? We said last time that if we're trying to predict a discrete y from n Boolean x sub i's, then we'll need, for Gaussian naive Bayes, 4n plus 1 for the prior parameters. But for logistic regression, we only need n plus 1. So it's got more parameters. Generally, all other things being equal, you think the more parameters, the more prone you are to overfitting. That's my rule of thumb. But all other things are not quite equal in this case. So actually, so let's take a more detailed look. But Nina, did you want to say? Okay. All right. So let's take a more detailed look. In fact, we're going to take a more detailed look by looking at this contrast between the generative naive Bayes classifier and the discriminative logistic regression along these two different dimensions. How restrictive are the modeling assumptions? One way to think of that question is, how well would it learn if we gave it infinite training data? Right? It can't learn what it can't at least represent. And so that might limit, even with infinite training data, what it can learn. And then the other dimension we'll look at is the rate of convergence. How quickly, as the amount of training data grows, do these two different algorithms approach their asymptotic infinite data solutions?
Can I make a comment, but this could be advanced?
Please.
So I guess it's true that we have the same, so it could be a bit advanced comment, but it's true that we have the same such, the number of parameters looks larger in naive Bayes, but the way we estimate those parameters, like for naive Bayes, we use maximum likelihood estimation. So it's a very specific way in which we estimate the parameters. And so that's why we need only log n samples, because there is only one specific rule that you have to care about. Like you care about, do we converge to, say, the mean, right? So it's a very, very specific rule that you have to care about, as opposed to logistic regression, where we have a much larger search space.
That's right. Right. So Nina's comment was right on target, that one of the ways in which things are not, all other things are not quite equal, is that in naive Bayes, we're estimating, getting maximum likelihood estimates for these different parameters.
That allows us to do the estimation with much fewer samples.
Right, and we can do that estimation with fewer examples than we can with logistic regression. And we'll take a look at exactly why. But in a sentence, the intuition is each of those estimates for the naive Bayes parameters are made independently using the data. Whereas if you think about the different W's in logistic function, it turns out the estimate of one of those parameters depends on the estimate you make for the other. They're not all independent. And so that changes the sample complexity.
Yeah, but if we didn't say, if we didn't use maximum likelihood estimate, but you would imagine you want to do naive Bayes, but you want to try various types of estimates for your parameters.
Ah, right.
Then you still need more samples. So it's also the fact that we use maximum likelihood estimation, a very specific estimation procedure, but also leads to fewer samples. Like what if you wanted to try maximum likelihood estimation and some other type of estimate also, then take the best somehow, then you need more samples for naive Bayes. So it's also a very, very specific estimation procedure. Not only the fact that they are done independently, but on each of them, in each of the axes, it's a very, very specific type of estimation.
Yeah, yeah, good point.
So we don't have to worry about so many rules kind of fooling us.
That's right. So it is a very specific type of estimation that, and that makes a difference. That's it. Okay, so what I want to do is first take a look at the difference between these two in terms of what they can represent. We had a very interesting discussion after class in the office hours, which I'll remind you were out in the hallway after class, trying to come up with some example where Gaussian naive Bayes would do well, or logistic regression would do poorly, and vice versa. And I just want to draw you a little picture that somehow came out of that discussion. So suppose I have some x1 and some x2, like last lecture. And these are continuous variables. You know, this could be your height, and this could be your machine learning grade. And the classification problem is to classify a Boolean classification over these x and y's. And we drew a particular distribution last time. Suppose this time I give you, suppose it turns out here's the true distribution of x given y equals 0. It looks like this. And so forth. Okay. So this will be p of x given y equals 0. And suppose here's the true distribution for p of x given y equals 1. This is an artist's conception of a Gaussian distribution. Okay, so let's think about how Gaussian naive Bayes would do on this and how logistic regression would do on this. Okay. So let's do as we did before. First of all, if we're going to train Gaussian naive Bayes, we have to estimate those different Gaussians, right? The probability of x1 given that y equals 0 and the probability of x1 given that y equals 1. So what will those look like if I have a bunch of data that's represented? Suppose I have infinite data, infinite training data that represents these two distributions. Then what will, so here's p of x given y equals 1. Then I guess p of x1 given y equals 1 will look something like this. Right, it's going to peak here. So this could be my p of x1 given y equals 1. And my p of x1 given y equals 0 will be slightly to the left. So it might look like this. Again, artist's conception. Okay, that's good. And what about p of x2 given y equals 0? Well, that'll just be this thing projected back here. Maybe that'll be a little wider. It'll still peak at the mean here. So this could p of x given y equals 0. And what will p of x given y equals 1 look like? You guys should be good at this by now.
Assuming that they have the same variance, it should be almost the same thing, but a little bit, with a little bit distance in the mean.
Yeah. Oh, I forgot to point out in this artist conception, these are identical means and identical variances. Okay, so it'll be the same thing. Okay, this is also p of x given y equals 1. Okay, well, right, and why is that? Well, you know, in terms of x2, if you want the probability of x2 given y0, you're interested in this distribution, you just integrate out the x1. So basically you project this back onto here, and all the probability mass in this distribution maximizes for x2 equals that value. And right, the only difference between these two distributions actually is an x1. This is just a translated version. So it is true that x2 is irrelevant here, right? It doesn't actually help you classify. Well, it's not quite irrelevant. Anyway, let's just say in terms of Gaussian naive Bayes, it appears to be irrelevant. Because p of x given y equals 1 is exactly the same distribution as p of x. I'm sorry, I should put a little 2 there. This is x2 that I'm talking about. Right? So that's clear? All right, so then given that, what's the linear decision surface that I will learn with this Gaussian naive Bayes classifier? Right, it's a vertical line. Where should I draw that vertical line? Well, it's just at this point where, right, when we evaluate things here, we're going to multiply, we're going to take the product over x1 and x2 of p of x sub I given y. x2 will be the same in both cases. And so the only one will be different is x1. So the linear decision surface for Gaussian naive Bayes is this. Okay, and for logistic regression, if I train logistic regression on this same example, what kind of linear decision surface will I get? Right, I saw somebody draw it in the air correctly. It'll be this. Right, why? Well, logistic regression is also constrained to come up with a linear decision surface. It's following that form. But during training, during the gradient descent procedure that's trying to actually fit the data, it's not paying attention to the conditional independence assumption. It's just estimating the weights of W0, W1, and W2 in a way that best fits, that maximizes the conditional data likelihood. So we'll get that. So I like this example because it's kind of a pure case where you can see the advantages that we get from logistic regression in terms of not being committed to that conditional independence assumption all the way through training. Okay, so so back to our discussion about what the trade-off is. Here's an example. We said we're going to look at this two ways. Here's an example where Gaussian naive Bayes, because it's using that conditional independence assumption all the way through, including it's estimating the parameters, but then it's using Bayes' rule with that conditional independence assumption. The whole model is committed to conditional independence. And so here's an example where logistic regression will be the method of choice for us. Okay, now, it turns out there's a simple way for me to keep this data that I have, but transform the problem so that Gaussian naive Bayes would work just fine. Does anybody see it? Yeah, right. Rotate the axes. So what if I defined a new x1 prime feature and a new x2 prime feature, and let me define, for example, oh wow, this is so, I love high tech, so we'll go to a new color, maybe green. So what if we say x2 prime is going to be x1 plus x2 over 2. So now, basically what I'm going to do is I'm rotating. So my x2 prime will be essentially this. Oops, bad. So here will be my x2 prime axis, and my x1 prime axis will be here. And now, oh, this is going to work great. Because now, in terms of the p of x2 prime given y equals 1 and 0, I'll have two different distributions. This one will be a Gaussian that peaks here on x2 prime versus there. And of course, in terms of x1 prime, I'll get a beautiful split as well. So I'll do just fine. So in fact, what this is illustrating is the fact, you can think this through too, that if you make the conditional independence assumption, then all of the joint distributions, this is actually the joint distribution in red of P of x1 and x2, given y. If you make the independence assumption, all of your joint distributions, if they're elliptical, the ellipses are going to be axis aligned. Right? They're going to be, the real ones won't be axis aligned, but the ones that you compute by saying p hat of x given y is p of x1 given y times p of x2 given y. This thing, this joint distribution, which will be the product of these two distributions, will be axis aligned. Meaning the ellipses will be, the major axis of the ellipse will be axis aligned, and the minor axis. Why? Well, if we're taking the product of a Gaussian with another Gaussian this way, you can see that for any point here, no matter if I have to multiply this Gaussian times whatever that probability is. And if I move to the left or right, I'm going to drop off. And similarly, if I'm here and I move up or down, I'm going to increase until I get to that point. So there will be a ridge here in the probability distribution that will grow until I get to the mean of that and then drop. So this is another way of thinking about the consequences of the independence assumption. Basically, in terms of Gaussian naive Bayes, it means that even if the real multivariate Gaussians are elliptical, not aligned with the axes, anything that you're going to compute based on this conditional independence assumption will be axis aligned. So this actually leads to another idea, which we'll pursue later in the course. Maybe sometimes it's going to be good for us to transform the space in which the data is represented. Right, here's the first simple example that shows some learning algorithms, like Gaussian naive Bayes, will work well or poorly depending on the particular way that we define x1 and x2, even if it's a simple rotation of the feature space, so that there's really no more information. x1 and x2 span the same two-dimensional vector space as x1 prime and x2 prime span. But somehow, if we happen to define our variables this way, Gaussian naive Bayes is going to be doing great. Yep?
So can we say, looking at this, that at the very best, the naive Bayes will try to reach logistic regression, can never go above it?
Can never go over what?
In terms of accuracy, can never go above logistic regression, because it looks like the maximum transformation that we can do is from can we say that it can only reach logistic regression?
Yeah, we can say that if we're making that assumption that sigma for x sub I and y sub k equals sigma for x sub I and y sub j, if we're making that assumption, then Gaussian naive Bayes will always be a line. And in this case, we're showing that logistic regression dominates. If we don't make that assumption, which we don't need to do when we train Gaussian naive Bayes, then we can get nonlinear decision surfaces from Gaussian naive Bayes. And that can sometimes beat logistic regression's requirement that it be a linear surface. So basically, that's the trade-off. So you just answered one of the key questions. Does one of these algorithms dominate the other in terms of the model bias, that is, its ability to express and converge to the correct decision surface? And the answer is no. In terms of, or or the answer is yes if we restrict that sigma ik equals sigma ij, then they're both linear decision surfaces and logistic regression will win. But if we define the more flexible Gaussian naive Bayes, which can get different estimates for the two sigmas, then there will also be cases where it can win.
In the large data case.
Where what?
In the large data case, when you have lots of data.
In the large data case, that's right. Right, so I'm just asking about model sufficiency for representing things. Whether it will actually get learned from a finite set of data is a whole nother, that's the other dimension we want to look at. Okay, good. So again, you know, this little mental picture carries a lot of information if you push it around. Okay, so let's then fill in the full story here. You can help me fill it in fact. So suppose I define, just to make our conversation clear, that there are two assumptions we can make. Number one, that x sub i's are conditionally independent given y. And assumption two is that these variances are independent of y. Okay, so I'm going to call Gaussian naive Bayes the more general of those. And I'll just define this other algorithm, Gaussian naive Bayes version 2, that also makes that restrictive assumption. Okay, so then the big picture is that means that this is going to be a linear decision surface. And this can be nonlinear. And logistic regression, of course, linear. So if we have infinite training data, and we happen to be in a world where both of our two assumptions are satisfied, then what's the relative dominance of these different algorithms? Right, then I guess we really want well, I guess what we can say is that GNB will dominate GNB2. But as we showed, we can't really say that. And I guess we could say that linear regression would dominate GNB2. For example, in the case we were just drawing on the previous slide. But we can't say that logistic regression would dominate Gaussian naive Bayes, because we might need a linear decision surface, or we might need a linear surface that doesn't obey the conditional independence assumption that the Gaussians are axis-aligned ellipsoids. Okay, what if neither assumption is satisfied?
In this case, I think, in this case, you can say, okay, GMB is greater than GMB2, and logistic regression is greater than GMB2 again.
Yeah, I think I agree with that. And that's about it. Is there anything else?
Well, the logistic regression, it would be greater than both of them. It will be the better classified than the GNB1 and GNB2.
Yeah, I'm just worried about logistic regression being restricted to a linear decision surface and GNB not. So I think this is probably all we can say. And if one is satisfied but not two, then I guess just as before, GNB is going to be better than GNB2, which is making that assumption, second assumption. But here I'd say also, if 1 is really satisfied and not 2, then I'm going to go with GMB over logistic regression, right? Because it can handle all kinds of decision surfaces that are nonlinear. Right? And as long as 1 is satisfied, those things are conditionally independent, then we're never going to get a case like the one we drew on the previous slide that violates conditional independence. Oh, that did violate conditional independence. Did you notice that? This violates conditional independence. Conditional independence says the probability of x1 given y is independent of the probability of x2 given y. That's not true. The probability of x1, if x2 equals this value, is this Gaussian distribution. But if x2 equals that higher value, the probability of x1 is a very different Gaussian distribution. So visibly, in this case, the probability of x1 given y is not independent of x2. It depends very much on what x2 is. Each of those x2s gives us effectively another distribution. Okay. All right. Yes?
So if, I was just assuming that the example that you were talking about is the case that, because the first case that you were talking about, both 1 and 2 are satisfied. I wanted to say that it shouldn't really matter because all of them have the same kind of simplification and all of them are satisfied. So why should we say that GMB is greater than GMB2 in this case?
Oh, that's good. That's good. You're right. We made a mistake, and I didn't make the mistake when I did my homework version of it. You're right. The first case, they are, if both are satisfied, all these things are equivalent because they will all be able to represent, oh wow, big mistake, okay. I'm going to change this because, we'll get in trouble if we post these slides. Thank you. Extra credit points. For correcting errors made in class, you get extra credit. Okay, so now let's look at, is there anything we can say about, that previous discussion was in the infinite data case. So is there anything we can say about how quickly, in terms of training data volume, these different algorithms converge toward their infinite data solutions? And there's an interesting paper by Andrew Ng, former student in our class, and Michael Jordan, that takes on this question. And I've posted the paper on our website. It's not, to be honest, it's not the world's best written paper, but it does have a very interesting result. So you're welcome to take a read of the paper. If you find that it's a little tough to get through, you're not the first one to have that impression. But it is a good paper, and the essence of the paper is this. What if we only have finite data? Then it turns out that Gaussian naive Bayes in logistic regression, they converge toward their infinite data estimates as the amount of training data grows, but they converge at different rates. So if I define epsilon sub a sub n to be the expected error of the learning algorithm A after I give it 10 randomly drawn training examples, then we can compare the expected error for logistic regression after n examples to the expected error for Gaussian naive Bayes after n examples. And they're different from their expected errors when n approaches infinity by quantities that have a different order. So if D is the dimension of X, the number of X sub i's that I have, and N is the number of training examples, then you can see that this one will require roughly N equal to D examples to converge, whereas this one will require roughly N equal to log D examples. And again, I'm not going to go through the math for this, but the paper is there if you want to take a look at it. But the interesting thing about this is that, so this is suggesting that, in fact, Gaussian naive Bayes moves more rapidly to the best estimates it can get, the infinite data case, requires, it converges in the number of examples more quickly to its asymptotic estimates than logistic regression does. And so if we take into account the fact that we don't have infinite data, what this is telling us is even though we might in principle say that, for example, all of these are equal if assumption 1 and 2 are satisfied, we might, in that case, actually, if we have finite data, prefer to use Gaussian naive Bayes because we expect that we'll be able to get better estimates of the parameters that way. So they did some experiments to explore this on some real data sets. And here they are for, I don't know, a dozen or so different data sets. These were taken from a repository. There's a UC Irvine, a repository of machine learning data sets, which you can download and play with yourself if you ever want to try out algorithms on a variety of data. They did this. They downloaded these different data sets. This one, for example, this one says voting records. This is breast cancer diagnosis, lymphography, and so forth. So these are different real-world data sets. And the dotted line curve is showing the error. So I guess each of these is the error as a function of number of training examples. And so, for example, here's logistic regression coming down and eventually getting a lower error as we increase the amount of data enough, whereas the other curve here is Gaussian naive Bayes, which dips quicker if we only have a little bit of training data, like 20 examples. Then we're getting a better lower error, and this is error over held out data, the actual error of the classifier. And so this is exhibiting just that phenomena that we thought we would see from the theoretical analysis. That as examples start to appear, the error drops more quickly for naive Bayes. But then in many cases, not all, once we have enough data, the logistic regression error overcomes that initial disadvantage that it had. Okay? All right, so that's, I think, about as much as we want to. Yes?
So, when we have asymptotic case, what will happen to overfitting error?
Actually, if we have infinite data, we won't have overfitting unless we have infinite parameters. If we have infinite data, we have effectively the whole, if we have infinite labeled data, we have the whole probability distribution given to us, and there is no risk of overfitting. But anytime we have less than infinite data, there is some risk. And so the overfitting risk decreases monotonically with volume of training data. Okay, so here's the bottom line. GNB2 and logistic regression both use linear surfaces, but Gaussian naive Bayes need not. If we have infinite data, we generally like logistic regression better than the linear decision surface version of Gaussian naive Bayes because it doesn't have to follow the conditional independence assumption during training. But it might still converge more quickly to its perhaps less accurate asymptotic error. And same with GNB. GNB, on the other hand, is more biased in the sense that it's following that conditional independence assumption, but less biased in the sense that it doesn't require a linear decision surface. So that trade-off can go either way. Okay. So if somebody asks you, some people often ask me after the first lecture of machine learning, why are we going to cover multiple algorithms in this course? Why don't we just have one good learning algorithm and use it? The answer you can kind of see here is that, well, there are different problem settings in which we're going to try to use these learning algorithms. And depending on the assumptions that we're willing to make about the data set, then we might actually prefer one algorithm or another. And in short, that's the answer. All right, so I'm going to leave Gaussian naive Bayes and naive Bayes and logistic regression behind and move on to another topic. Any comments or questions before we do that? Okay. So let's talk about regression. Regression, you're going to find, is really easy because of all the stuff you already know. Regression simply, I don't even know how it got that name, but what it refers to is function approximation. Again, we're trying to learn a function from x to y, but y happens to have a real value instead of a discrete value. And we call those regression problems.
The name logistic regression is a little bit confusing.
That's right. The name logistic regression is a little confusing because there we have discrete valued y's. But there are plenty of, it's easy to make up prediction problems, function learning problems where y is real valued. So we're interested in how can we do that. And here's the approach we're going to use. It's the very same approach we've used for everything for the last week and a half. Well, if we want to learn some function from x to y, and we're given some training examples, training example 1 through n, then let's do what we've done before. We'll choose some parameterized form for the probability of y given x. Of course, y now is going to be a continuous random variable, so we'll have to take that into account when we're making this up. And then we'll just derive a learning algorithm. And for example, we could again use maximum conditional likelihood estimation or the maximum a posteriori probability estimate where we have a prior on our parameters. But it's exactly the same strategy we're going to use. So then the first question becomes, how can we, what kind of probabilistic model do we want to set up here? And so let's look at linear regression, a simple case where we just have one variable x and one variable y. And I've plotted some training examples there. And I just want to learn a linear function for predicting y from x. But now, since we're taking this probabilistic tack, that means I need to talk about, I need to make some assumption about what is the form of p of y given x. And so the assumption that I'm going to make is that the observed y is the result of some deterministic function that operates on x and gives me a value y. And then the noise-free value of that function is perturbed by adding in a random variable epsilon, which is noise. And furthermore, I'll assume that that noise itself is just a Gaussian distribution with mean 0 and some variance. Okay, so what that means is if I'm going to, for example, generate an example for that x, then I'll predict, well, first I'll generate a value of the true f of x. Suppose this red line is the true f of x. Then I'm going to get that value y. But then I'm going to add in some noise. That noise will come from a random draw from a Gaussian distribution with 0 mean and variance sigma. So it's, then I'll add to that maybe some noise and get this point. Okay. So given that, then I can realize that, well, this epsilon, of course, is a random variable. And since y is a function of that random variable, y is also a random variable. And in fact, y, the probability of y given x, is just this f of x plus epsilon. Well, that means y is really just going to follow a normal distribution whose mean is not 0, but whose mean is f of x. And then, since we're adding 0 mean Gaussian sigma noise, y itself will follow a normal distribution centered at f of x instead of centered at 0. Right? So put another way, for this particular x, there's some distribution, some Gaussian distribution of y's that I might observe if I give this x as a training example and ask for the y. It'll be a Gaussian centered at the true f of x, but depending on what draw of random noise I get, it'll be somewhat different according to a Gaussian. So that green picture corresponds to just saying y itself is following a normal distribution with mean f of x. All right. And of course, the expected value of y is just f of x. That is, if I hold x constant and draw many samples of y, I'll be sampling that Gaussian distribution, and the expected value of a Gaussian distribution is just the mean of that distribution. And so the expected value of this thing will be f of x. All right, so why are we saying this? This is just saying what I just said. So now let's talk about training it. We have a probabilistic model for p of y given x. We know, because we've been through this several times now, that a good way to design a learning algorithm is to start with a probabilistic model, pick one of our principles, maximum likelihood, map, and then go through the math to figure out what would be the way of choosing a value for our parameters that maximizes the likelihood or the posterior probability. Okay, so let's do that. In our case, just like before, one new assumption here. Suppose, in this case, when I say linear regression, what I mean is that we're going to estimate our function by saying y equals some w0 plus w1 times x. Linear regression. We're going to estimate a linear function. And so now my probability of y given x is just a normal distribution whose mean is f of x, that is the true w0 plus w1 times x, and whose variance is sigma. How can we learn this? Well, if we want to maximize, if we want to choose our weight vector, w0 and w1, to maximize the conditional likelihood, what is the conditional likelihood? Well, if I'm given a set of training examples where I use L here to refer to the Lth training example, this is the Lth training example. That's what that superscript means. Then the formula for the conditional likelihood is simply the product over all my training examples of the probability of that observed y value on the Lth training example given the x that I observe. That's the conditional likelihood part of it. And whatever weights W I have.
It doesn't really matter, but just are you thinking about one dimension here, only one feature, or are you deriving it in general, three features? Just one feature?
In this case, we're assuming there's one feature, but we have two W's. So in this case, W is actually this vector of two parameters.
So dimension is one, really.
Pardon me?
Thinking about D equals one.
Sorry?
You are thinking about D equals one, the dimension is one, or it's just general D?
Oh, this will be true in general.
Sure. Yeah,
And the example that I'm looking at here, we just have 1x. But this is going to be true in general, of course, right? If x is even a vector instead of, in general, x will be a vector, y will be a single value, a scalar. And then we'll be predicting a single scalar from perhaps a vector of x's. If we had a vector of x's, we'll have a W2 and so on.
the very first equation suggests D equals one, the very first equation on the slide.
Right, then that top one would be different too. Okay, but in this example, I'm just assuming we have 1x, and we're just predicting y as that function of x. So then I could just write down the conditional likelihood. This is the same expression we wrote when we did logistic regression. And as it turns out, just as in the case of logistic regression, it's a little easier to work the math if we, instead of maximizing that, try to maximize its log. Just makes the arithmetic easier. Maximizing this quantity is identical to maximizing that, but the arithmetic is easier here. And here, of course, my probability distribution on y given x is exactly this. This is just the formula for a Gaussian. And for the mean, I've plugged in f of x, which in our case is, well, given f of x given w, which in our case is just w0 plus w1x. Okay, so it's just a Gaussian distribution where I've set the mean to be my predicted value of y. And this is the observed y on the, well, if I want to make this to talk about particular training example, then I'll say the probability of the Lth y given the Lth x is this, where this is w0 plus w1 times the observed Lth x. Okay? Okay, so this is just the same maximum conditional likelihood thing we've been doing, except that now we have a different form for p of y given x. It's not that logistic function that we were talking about last lecture. Now it's this function instead. But just as before, now if we want to, let's say, find the set of weights, W, which maximize this quantity, or which equivalently maximize the log of it, then we can just plug things in and solve for example, a gradient descent rule, to maximize that likelihood. Okay, so let's do that. So again, this quantity is going to be W0 plus W1x. And what I want to do again is I want to find the weights W0 and W1 that maximize the log of the conditional likelihood. And so I could write out that expression, given that we agree that P of y given x is this Gaussian. So let's do that. So then argmax over W of this thing. So W which equals the argmax of that, I can write it out this way. It's not going to be the sum of the log for each training example that I have of the log of this P of y given x. So what is that log? Well, the log, so I have to take the log of this quantity. So, but that's just the log of the first term. Plus the log of the second term. Yes? Oh, to red, is that more visible? Sure. Is that better? Good. Let me do it then. Okay, so now I'm going to take the log of this thing plus the log of the second term. What's the log of this? Fortunately, the natural log of e to something is the something. So that's just plus minus 1/2 of y minus, and I'm going to plug in instead of f of x there, I'll plug in the real quantity. It's W0 plus W1 x for the elf training example. And this is y for the elf training example. Squared. I guess I have to get a sigma in there. Okay? Oh, a minus, yeah. That was minus 1/2. Thank you. Okay, so now if I want to maximize this using gradient ascent, or gradient descent, it means I'm going to want its derivative, but there's a point I want to make first. Well, first let's just notice that this quantity itself is independent of my w's. So if I'm going to pick w's that maximize this expression, I can ignore this. So it's really just, what I really want is just the argmax over w of this second expression. Cool. Okay, and well, let me put it this way. This is a negative quantity. This is going to be a negative quantity because this square is always going to be positive, of course. So this is negative. So I could just rewrite this as arg min, get rid of my negative sign, of oh, let me bring the sigma out. Good. That's nice and clean. Okay, so what I'm saying is, if I want to choose my weights, W0 and W1, according to the maximum conditional likelihood principle, then that's equivalent to saying that I want to choose my weights to minimize, oops, where'd I leave? I left out my sum. You guys should have caught me. Sum over the training examples. If I want to maximize the conditional likelihood, that's equal to saying that what I want to do is minimize the sum over the training examples. That's again what L is the superscript for the Lth training example. I want to minimize the sum over the training examples of the squared error in my prediction of Y. So if you've seen linear regression before, or many kinds of curve fitting that people do, often the lecture begins by saying, let's minimize the sum of squared errors. Let's find the curve fit that minimizes the sum of squared errors. It's a reasonable thing to do, and then the course goes on from there. But here you can see that, in fact, a good justification for that is that minimizing the sum of squared errors is identical to maximizing the conditional likelihood of the observed y's given the observed x's under this pretty reasonable probabilistic model that we're assuming here. That is, our data is perturbed by zero mean random Gaussian noise. So this is very nice. I don't know if people have seen this idea before of minimizing sum of squared errors during curve fitting. It's very pervasive. And here, fortunately, we can see it's just a simple consequence of choosing one of our two standard principles for doing learning. Okay. Now you can also easily derive the gradient rule for this. For the gradient rule, what we want is to get the gradient of this conditional maximum likelihood, that's this quantity, with respect to each of our w's. That is the partial derivative of this with respect to the w's. And for example, if I want to get the partial derivative of this, I'll call this L of W, the log likelihood of W. If I want that partial derivative of that thing with respect to, say, W1, for example, that's this quantity. What's that derivative? Can you see it? And it's going to be 1 over sigma squared times 2 times this whole quantity. Times the derivative of this, again, this quantity with respect to W1. Oops. Jeez. Ah! Something horrible is happening. Wow. Okay. See how much more is coming. Then we also need, this is times the derivative of this quantity with respect to W1. And that derivative is simply XL, right? Minus XL. Did I get my minus right? It's the derivative, chain rule of calculus, right? The derivative of something squared is just 2 times that thing times its derivative with respect to the thing we're interested in. And I guess I do have a minus there. So it's good that I moved that minus up here. Sum.
Sum over all training.
Oh, sum over the L's. Thank you. I keep forgetting that sum. Sum over L. Okay, so there it is. So now we could do gradient descent. I say descent because now we're trying to minimize this. With respect to, we can do gradient descent to train a linear regression system. And that gradient descent is the same as gradient ascent on the conditional likelihood. And it's equal, because we've shown it, to minimizing the sum of squared errors between the line that we end up estimating with W0 and W1 and the observed data. So this is kind of fun because it turns out most linear regression systems, we don't always think of them as probabilistic approaches to machine learning. In fact, they don't internally manipulate any probabilities at all. They're just, for example, we could do gradient descent like this to do it. There's no probability in here. There are just some weights and some x's and y's, and it's happening. But as an observer, we can look in and we can say, well, even though it's not directly internally manipulating probabilities, we can interpret this as a probabilistic approach, which is maximizing the conditional likelihood of the data. And in fact, quite a few algorithms are like that. Neural networks are like that. And most things that go under many things that go under curve fitting, for example, that are trying to minimize sum of squared errors, you can think of with the same kind of analysis. Okay, so that's the main things we wanted to cover. Oh, we just did all this. Oh, we could do a map estimate instead, and it won't even be very different. So we just solved for maximizing the conditional likelihood. If instead of that we want a map estimate, we should put some kind of prior on our weights W. And again, if we have a set of weights, we can just say, well, let's assume each weight we put a prior which is zero mean Gaussian. And it turns out, just as we were able to show that maximizing the conditional likelihood equals minimizing the sum of squared errors, that maximizing that the probability for that Gaussian ends up being the same as, oops, I should have a minus in here. It's the same as adding in a penalty term that pushes the weights towards zero. And this would be a good homework for you to do on your own to show that if you put a Gaussian zero mean prior and you work through things, then you find out that it's equal to adding a term like this in the quantity that you want to maximize. It's not hard to show. Okay, so this is it for regression. The beautiful thing is it's easy to get regression because you already knew 90% of what you needed to know. We can do maximum likelihood estimates to do linear regression. It's equal to minimizing the sum of squared errors. We can do map estimates, which means to minimize the sum of squared errors plus the sum of the squared weights. Again, learning is an optimization problem once we choose what objective we're trying to optimize and then solve for the W's. And again, if we want, we can use gradient descent as a general purpose technique for solving that. In fact, when it comes to linear regression, if you have a relatively reasonable number of x sub i's, then there are faster ways than gradient descent to solve it. There are matrix inversion techniques that can solve it. But in fact, if you get big enough dimensions, even for linear regression, it turns out that inverting humongous high-dimensional matrices is very expensive. If you make the dimension high enough, even for linear regression, gradient descent is a very competitive technique for solving the problems. So, in fact, also notice that almost nothing we said here required that f of x be linear. If I asked you, for example, on a homework or a midterm, to instead consider a problem like, oh, I don't know, f of x, I'll say y, equals w0 plus w1 x1 plus w2 x2 plus w3 times x1 times x2, you could probably derive a great gradient descent-based machine learning algorithm, which is guaranteed to maximize the conditional likelihood of that vector of w's given the observed data. And that would be a good thing for you to think about. If you can do that, then I think you really have your head around the whole process that we're talking about here and the whole line of reasoning that we're talking about. Okay, so that's what I wanted to say for today. Comments? Questions? Okay, see you next time.